purpose for today's lecture is to start to do probability. So only 25% of you have taken probability with me. I'm not sure about who's watching this at home. And so what I want to do is I want to do the bare minimum we need of probability to get to the proof of the central limit theorem and see exactly what is needed to make the proof rigorous in general, or at least in a large class of distributions. How many of you are comfortable with basic probability? Sums of independent random variables, convolutions. Okay, so let's do a quick probability review. So we say x is a random variable with density f of x if two things are true. Fx of x is greater than or equal to 0, and then the integral from minus infinity to infinity of fx of x dx equals 1. I'm not going to do things in as great generality as possible. I'm going to assume my distributions are continuous. You could, of course, have distributions that are supported on countable sets. You could have distributions that are a mix. Let's just try to keep the notation simple. Opposite of keeping the notation simple, I like to have subscripts on my densities to refer to the random variable under discussion. This is extremely important when you start combining lots of different random variables so that you can just quickly glance down and see what is going on. Note that one of the reasons we care so much about integration is integration gives us areas. So the probability that x is less than or equal to a would be the integral from minus infinity to a of fx of x dx. And we often write this as the cumulative distribution function at a. So this is the cumulative. Somebody sneaking in? Yes, but not so well. Distribution function. So you should time somebody to be opening that door so I'm distracted. Sorry. No problem. So this is the cumulative distribution function. This is why we care so much about Calc 1. Calc 1, Calc 2, they give us integrals. Integrals give us areas under curves. Areas under curves correspond to probabilities. Now, one of the things that you have to think about is in Calc 2, you learn how to integrate. Or you think you learn how to integrate. It's actually the big lie of Calc 2. You actually do not know how to integrate in general. We have to work really hard to give you functions that you can integrate. Almost every density cannot be integrated in closed form. Fortunately, in many cases, we don't actually need to do the integration in closed form because we immediately take a derivative. So the cumulative distribution function is the probability you take on a value this large or smaller. You then find the density by taking the derivative. Well, if I integrate and then immediately take the derivative, I'm just getting the integrand. So you might integrate this from minus infinity to, say, t, and then take the derivative. Now, if we want two random variables, say x and y, are independent, then the probability that x plus y is less than or equal to z would be the integral x1, well, let's say x goes from minus infinity to infinity, f, y, and then, well, here, let's do it this way. Y goes from minus infinity to something, the density of x, the density of y, dy dx. So if I want the sum of x plus y to be at most z, how large can y get? So how large could y get? I need my bound of integration. So x plus y has to be at most z. Z minus x. We're not going to worry now about justifying everything. But when I have my expression like this, I want to first integrate with respect to y. And I'll get the cumulative distribution function of y evaluated at z minus x. Because this is the probability that y takes on a value at most. And then if I take the derivative with respect to z, that will give me my density function. So typically, we'll let z be x plus y. This is the cumulative distribution function of z. This is the probability that a value of z is at most little z. So we would then get the cumulative distribution function would be the integral x goes from minus infinity to infinity, fx of x, cumulative distribution function of y at z minus x dx. I should, of course, evaluate this also at minus infinity. But what's the probability my random variable is minus infinity or smaller? 0, right? We don't allow our random variables to take on the values plus or minus infinity, so the probability that's minus infinity or smaller is going to be 0. Now I just want to differentiate this with respect to z. How should I differentiate this with respect to z? What should I do? How can I take the derivative of this with respect to z? The left-hand side is easy. It's just... But how do I take the derivative of the right-hand side? What do I do? Non-integration by parts. I have d by dz of this expression. I have the derivative of the integral. So the derivative of the integral is the integral of the derivative. I want to pass the differentiation through the integration. This is where you need results from real analysis. How can I justify passing the derivative through the integral? Well, fortunately, my functions here are non-negative. This function is between 0 and 1. Everything is well behaved. You can justify passing this in. And this is what's so wonderful. When I take the derivative of this, remember, I don't necessarily know what the antiderivative is of my density fy. But I'm immediately taking its derivative. And I know the derivative of the antiderivative of f of y. The derivative of the antiderivative of f of y is just f of y. So we then get it's the integral x goes from minus infinity to infinity, fx of x, fy of z minus x. And now we need to take the derivative by the chain rule of z minus x with respect to z. What's the derivative of z minus x with respect to z? 1. And so if you think about it, this is a very reasonable definition for the probability that x plus y equals z. I take some value for x, and this is the probability density that it happens. The corresponding value for y must be z minus x. And so I then just integrate over all possible values of x. So this is a very reasonable formula at the end of the day. So this is called a convolution. So I apologize for those of you who have seen this multiple times before, but convolution. So f star g of x is the integral from minus infinity to infinity of f of t g of x minus t dt. In everything we do, f and g will be densities. For us, f and g are densities. This is, of course, true in much greater generality. But if f and g are densities, we have a lot of nice things going on here. The first thing is that these functions are integrable. They're non-negative. Now, they may not be in L2. If you've heard of spaces L1 and L2, the square of these functions may not be integrable. For instance, f might be like 1 over square root of x from 0 to 1. If you integrate that, you get x to the 1/2. That's fine. But if you square it, you get 1 over x, which is not integrable. So we don't necessarily know that the squares of these functions are well behaved. But we do know the integrals of these functions are well behaved. Now, what do you think the relation is between g star f and f star g? What do you think the relation should be? So if we think about this, this is the random variable, say, x plus y. And that would be the density of the random variable x plus y. On this side, what would this be? Y plus x. So at least in the case when we're dealing with independent random variables, this is true. It's true in greater generality. You do a change of variables. And if you do a change of variables, you can show that these two are equal. You also can get associativity f star g star h. It doesn't really matter how you put the parentheses in. You're just using the associativity and commutativity of addition. So inherits properties from addition. This is nice. Whenever you have a new operation, if you're building it off of old ones, it's nice when your old properties survive. Addition is commutative. Addition is associative. This new convolution has these wonderful properties. Unfortunately, if you look at convolutions, it's not that clear what is f star g. Right? How would you actually calculate f star g? What would you have to do? You'd have to integrate, which we've just learned, or I've tried to explain to you, that we don't know how to integrate. Now, if you want to see some good integrals today, the math colloquium is going to be on the trillionth digit of pi. And it's going to involve things like the Cauchy distribution and whatnot, and how you can use that to jump to the trillionth digit. It should be a very good talk. But in general, we can't integrate. So the fact that we can express these densities in closed form, this is nice, but it's not necessarily useful. It turns out that there are certain processes that convert convolution to regular multiplication of new functions. So we have this transformation where we can transform f to a new function, g to a new function. And the transform of the convolution is the product of the transforms. And I'm not saying what it is. So the transform of the convolutions is the product of the transforms. Does this remind you of anything you might have seen in a math class? The word transform looks familiar. So if you want, you can actually view it if you want as the Fourier transform. Yeah, the Fourier transform converts convolution to multiplication. But does this seem like anything you've seen before? If you want, it's not from a math class I've taken. Abstract algebra, yes. What does this kind of remind you of? Homomorphisms. And you have maybe a group, and you have the image of the group under a homomorphism, and you want the operations to be respectful to the transformation. Do you think that this is a group? Is it closed? Is the convolution of two densities a density? Yes. Do we have inverses? Do we have an identity? So this is not a class in abstract algebra. I'll let you think about stuff like that as to, is it actually a group, or does it just have a lot of properties similar to a group? If it does have an identity element, what would be the identity distribution? But this gives you some idea of why we actually construct a lot of these transforms, is that to take quantities that naturally arise and convert it to a more useful way of attacking. Okay, so in a probability distribution, one of the most important things is the moments. And so the expected value of x to the k is equal to the integral from minus infinity to infinity of x to the k times the density. Unfortunately, the moments don't always exist. So for example, if you take fx of x is the Cauchy distribution, 1 over pi 1 plus x squared, clearly the second moment doesn't exist. If we integrate x squared, well then we'll have x squared times 1 over x squared. For large values of x, what does the integrand look like? Yeah, well, 1 or 1 over pi squared, depending on how you want to view it. So this would look like the integral from minus infinity to infinity of 1 over pi x squared over 1 plus x squared dx. When x becomes very large, the integrand is going to look like 1 or 1 over pi. It's going to blow up. So unfortunately, moments don't always exist. And so since moments don't always exist, we have trouble. Wow, so the batteries are not even saying charged. New batteries that were working. All right, so unfortunately, just because we can write down the integral for a moment does not mean that the moment is finite. But in many situations, the moments will exist and the moments will be finite. And the if you know the moments, you know the density. Does that seem reasonable? That if we understand what the moments are, we should understand what the probability distribution is? Does this seem similar to anything you might have seen from real analysis?
Taylor series.
Taylor series. So, similar to Taylor series. Does this make you feel happy or sad?
Happy.
Okay, why happy?
Because we've been doing a lot of things with Taylor series.
Taylor series are good. But let's think about convergence issues and uniqueness issues. If I give you a real analytic function, a function that's infinitely differentiable, is it uniquely determined by its Taylor series?
Is the function real analytic or is it infinitely differentiable?
Oh, good. So yes, good. Because I said real analytic, it is by definition given by its Taylor series. I want a function that's infinitely differentiable. Sorry, thank you. Yes. I give you a function that's infinitely differentiable. Is a function that's infinitely differentiable given by its Taylor series? Or is there a very bad function we saw earlier in the semester as the poster child of why real analysis is so much worse than complex? Does anybody remember this horrible function? It's either a bad function if you want things to be well behaved, or a good function if you're searching for counterexamples. So we take f of x is, everybody remember? I'll give you half of it. 0 if x equals 0.
E to the 1 over x squared?
Almost. You're extremely close. It's almost e to the 1 over x squared. You're off by a very small amount. What happens as x approaches 0? What does this look like?
1.
No. So let's say x is 1 over a billion. This becomes e to the 1 over a billion squared. This becomes e to the billion squared.
Yeah, negative.
So negative. So if we take this function, all of its derivatives exist, and you get the nth derivative of this function at 0 equals 0 by L'Hopital. And this tells you why real analysis is so hard. Here is a function that's infinitely differentiable, and if you were to write the Taylor series, since all the derivatives are 0 at 0, the Taylor series would be identically 0. The only place where the Taylor series agrees with the original function is at x equals 0. Well, given that we write our Taylor series as f of 0 plus a multiple of x plus a multiple of x squared plus a multiple of x cubed, we force ourselves to agree at 0. This is no great achievement to agree with the function at 0. We forced ourselves to agree with the function at 0. You need to agree at one other point in order to have something non-trivial. And we don't have that. So this example is why complex analysis is so much better than real analysis. Complex analysis will not allow us to look at functions like this. So what must be true if we looked at this function complex analytically?
It's not holomorphic.
It's not holomorphic. So if this function were holomorphic, at the origin, then it would be differentiable, then it would be infinitely differentiable, and then we know holomorphic means analytic, which means it would have to be given by its Taylor series. So this function cannot be holomorphic. So somehow when we view this function in the complex plane, even though it's well behaved on the real line, something goes down when we go to the complex plane. What point should we choose for this function where things will blow up? Where should we evaluate this? Yes?
On the imaginary.
If we evaluate this on the imaginary axis, then we're going to get trouble. So if we look at x equals it, then we get e to the negative 1 over negative, so we get e to the 1 over t squared. And that's going to blow up. Okay. So this gives us some sense of how dangerous things can be when we look at functions that are well behaved on the real line, but not well behaved when we extend. So when we're trying to develop a theory of probability, for the most part, physicists, excluded, we like to look at, nice real valued functions. The physicists often look at the modulus squared, and they'll have a complex valued function, and they'll look at the modulus squared because that'll be a real quantity, and they'll integrate that, and then everything will be fine. But it turns out you really need to understand complex analysis to look at a lot of this stuff. So the problem is, sadly in general, it is not enough to have a function that's infinitely differentiable. The Taylor series will not uniquely determine the function. Well, if moments are similar to Taylor coefficients, you would love the moments to uniquely determine the probability distribution. Similar to Taylor coefficients, the moments will not uniquely determine the probability distribution unless you have a little bit more information. So when we calculate the moments, we typically think of k as a positive integer. So the expected value of xk is the integral from minus infinity to infinity, x to the k, fx of x dx. Usually k is in 0, 1, 2, etc. Even if all the moments exist, that is not enough to uniquely determine the probability distribution. What do you think I would need rather than just all those k to work?
Some negatives.
Some negatives. That would still be a discrete set. And a discrete set is not going to be enough for us. So remember, you're experts at complex analysis. We've already done a graduate course in it. We moved at a really good rate.
Maybe this is just guess, but maybe we want a sequence that accumulates.
Ah, maybe we want a sequence that accumulates. Why might we want a sequence that accumulates? It's a good guess. What theorem do we have about accumulations?
In complex analysis, we can take n if it's a continuation.
So we can take another continuation, but there's something really nice if you have, say, two functions that agree on a sequence that accumulates. What do we know about those two functions?
They're homomorphic, they agree everywhere.
They agree everywhere. So the whole issue is that, maybe we haven't uniquely specified our function. Do we know any way to have a sequence of data uniquely specified? Yes. So points of accumulation lead to unique specification. Okay. Have to remember to dot the i's in a complex analysis class. So if we have a sequence that accumulates, then there's a really good chance that we can win. Now here's the interesting thing. What would you think would be a really good sequence of moments to accumulate? There's infinitely many choices, so give me a choice.
1 over n.
1 over n. So one thing is a possibility is a sequence that accumulates to the 0th moment. Or maybe things that accumulate to the mean, or to any finite moment. Or maybe just every moment in the interval is 0, 2. You have lots of different choices. What's fascinating is we're not talking about any complex moments. We're only talking about real moments. Why? Well, if we can extend our function to a complex valued function, even if we only look at real moments, right, we know it's lurking in a complex space. So, can suffice to only study real moments if the complexification is holomorphic. So again, there's not quite uncountably many things we could do in this class, but effectively there are. There are so many different ways we can go. What I want to do is I want to give you a sense of why did we prove all these theorems in complex analysis? How can we use them? why are you taking this course? What are you getting out of this? We saw how a lot of the ideas are extremely powerful in analytic number theory, in counting primes. Today, we're starting the tour in probability, and we're going to see how these techniques from complex analysis can be applied, amazingly, in a situation where nothing is complex. So what's really happening is lurking in the background are the complex extensions of the densities. And those complex extensions, that's where things are going to be nice. Okay, any questions about any of this? So let's define the moment generating function. Moment generating function, MGF. So there's a lot of different functions you can do. So we'll have the moment generating function of x evaluated at t. It's going to be the integral from minus infinity to infinity e to the tx fx of x dx. And so this will be the moment generating function. When you look at this, what makes you happy, what makes you worried? Yes?
In the numerator, is that, or in the exponent, is that?
Oh, sorry, that should be a regular x. That should be a regular x, yes. It's just fun writing the fancy x's. But I must resist the temptation. What makes you worried when you see this definition?
Don't really like seeing e to the x when you're integrating.
Yeah.
to infinity.
This gives you exponential growth. Yeah. Integration is hard enough as is with functions that have nice decay properties. Shoving in something that's exponentially growing is bad. But, well, hopefully a lot of our probability distributions are either decaying faster than exponential, or maybe they only even have finite support. Typically, what we're going to need in complex analysis for things to work is for these functions to exist in a neighborhood of t equals 0. So we're going to want to go a little bit in both directions. Now when you look at this, going in the negative direction, you have exponential decay from this. But, well, what's our growth rate here? A lot of distributions don't take on negative values. We might be looking at, count information. And if you want to know how many times something happens, the number of times something happens is not going to be a negative number. Okay? So we always have to worry about convergence of this. And what might happen is this function might only converge for certain values of t. And we typically want convergence for, say, the absolute value of t less than delta, and we'll always assume delta is greater than 0. And if something like that happens, then we would have the moment generating function would exist in a neighborhood about the origin. And the hope is that we can understand things in that region. Okay, now, this is where things get tricky because this is a probability topic, but it's being discussed in a complex analysis class. As bad as the physicists are with respect to the mathematicians in terms of notation, there are also some issues within subfields of mathematics. One of the problems with the moment generating function is it does not always exist. And when you're looking at objects, it's really nice if the objects exist. There is a very close cousin of the moment generating function which always exists. And you just have to do a small little tweak to where you evaluate it. You don't evaluate it at t. And the idea is where you might evaluate it at. IT. So we call this the characteristic function, or if you have a different accent, the Fourier transform. But of course, the Fourier transform is a misnomer. Now, I am wearing my Ohio State shirt. The reason I'm wearing this is because it's not that I'm superstitious. It is a fact that Ohio State does not lose in weeks when I wear this shirt on a Monday. So, have to continue to keep wearing this on Monday. Does anybody know the full name of Ohio State?
The Ohio State.
The Ohio State University. Not a Ohio State University, the Ohio State University. I should not say the Fourier transform. There is not a unique Fourier transform definition. There's at least 3 definitions of the Fourier transform that have advocates. So I should really say a Fourier transform. The one we typically like to use is phi, the characteristic function, at t would be the integral from minus infinity to infinity of e to the I tx fx of x dx. So there are two advantages to this for us. The first is this is a class in complex analysis, and I'm at least finally using the square root of -1. So in terms of trying to justify to you why I should be allowed to give you this lecture and not have you go to Professor Morgan and complain that this was, false advertising, at least we finally have an exponential involving an I. So I'm off the hook. The other thing is this integral will always converge. And the reason is if you take absolute values, since t and x are real, what's the absolute value of e to the itx? 1. And since this function is non-negative, it integrates to 1 and its absolute value is itself. This always exists. So this is one of the biggest differences between the characteristic function and the moment generating function. The characteristic function always exists, you can work with it. The moment generating function does not always exist, but it's a little bit more comfortable in terms of what it represents. If you put in the Cauchy distribution here, the 1 over 1 plus x squared, you're definitely not going to have convergence for t in the neighborhood of the origin because e to the tx decays exponentially in the negative direction, grows exponentially in the positive direction. Since 1 over 1 plus x squared is decaying polynomially in both directions, if you go off to to positive t, this will explode. So this does not always exist. Does not always exist. Okay. So I know a lot of you have not taken probability before, but you've at least looked at math phrasing. What do you think the moment generating function gives you? Well, the moment, right? Now again, we have given you, secant is 1 over cosine. So, we do have a history as mathematicians of having bad nomenclature. But, if something is called the moment generating function, it should hopefully give you the moments. So let's look. So the moment generating function x is going to be the expected value of e to the tx. This is going to be the integral from minus infinity to infinity of e to the tx fx of x dx. I want to get the moments. The moments, the kth moment would be the integral of x to the k. Any thoughts, if you haven't taken probability with me, on what we should do at this point? I want to somehow get integrals of x to the k times the density. I don't have x to the k, I have e to the tx.
Again, do you mean a regular x and the exponential?
Yes, that is a regular x.
Above.
Over here?
Yeah.
No, that's actually the correct x,
Okay.
because that's my random variable. I'm taking the expected value of this quantity, which means integrate e to the tx against the density. I don't want to integrate the exponential against this. I want to integrate polynomials. I want to integrate x to the k.
Put a log in the exponent somewhere.
But if I change variables, then I'm changing the density as well. So I don't want to change variables. What do you think of when you see e to the tx? What does that mean to you? The Taylor series. So let's put in the Taylor series. We'll have a sum, n goes from 0 to infinity, of t to the n, x to the n, over n factorial, fx of x dx. Now what's your temptation? Yes, switch them, right? When in doubt, either change variables or switch orders of integration. We really don't learn that many things in Calc 3. Can we switch the orders of integration, or are you a little bit worried? Well, if we want everything to be well behaved, we'd have to put in absolute values. And so unfortunately, if we put in absolute values, we can't exploit cancellation, There'll be issues with odd values, maybe, even values, maybe things are growing too much. So we're going to need to have enough decay so that this is fine. So this will not always be possible. If you try to think about what's going on with the moment generating function versus the characteristic function, the characteristic function has an ITX. Does that mean I can just expand this out here? No. I'll not necessarily have a series that will exist. But let's just pretend we can do this. Alright? So we'll have a sum, n goes from 0 to infinity, x to the n over n factorial, integral from minus infinity to infinity, I'm sorry, t to the n. And then we'll have x to the n fx of x dx. And that will be the nth moment. And so what we would get is we'll get a sum, n goes from 0 to infinity, of the expected value of x to the n over n factorial times t to the n. And this is why we call it the moment generating function. If you look at the Taylor series expansion of this, you essentially have the moments of your distribution. And if you were to take the nth derivative and then evaluate the nth derivative at 0, when you take the nth derivative, an n factorial comes down from the t to the n. The only term that survives is the t to the n. And so you would get that the moment generating function, take its nth derivative at 0, is just the expected value of x to the n. And this is why we care so much about this function. It may not always converge. And that's a problem. But in a lot of the probability distributions we're looking at, we will have convergence. It's not going to be a huge issue. Okay? So today is, basically the day of the preliminaries, of getting ourselves ready so we can start to apply complex analysis. Essentially, the idea is the following. If I want to study, if I study sums of independent random variables, so we're going to make things a little bit nice. So central limit there. x1 through xn IIDRV. This means independent, identically distributed, random variables. We can let yn be their sum. Okay. We'll assume each has mean, mu, and standard deviation sigma. Has everybody seen mean and standard deviation? If not, please speak up. Everybody's comfortable with mean and standard deviation? Okay.
What does it say right before the parentheses?
Right here? IIDRV, independent, identically distributed random variables. Independent, identically distributed. It's one of the new words in probability. And so the mean is just the expected value of x, and the variance is the expected value of x minus mu squared. It's a measure of how spread out things are. What we can do now is we can look at what we'll call Zn will be x1 plus xn minus n times mu. And now let me see if I can get this right. N square root of n sigma squared. Okay. The idea is to look at the right quantity. So if we look at y, if the mean isn't 0, the average value of y is going to be growing just because we're adding more and more quantities. So we want to normalize things. If we subtract off n times the mean, if each one of these we expect to be of size mu, if we have n of them, we expect their size to be n times mu. And what we're using here is we're using what's called linearity of expectation. The expected value of a sum is the sum of the expected values, even if things aren't independent. So So again, this is not a course in probability. If you haven't taken a course in probability, I recommend you do so. I'm just trying to give you enough of a feel and flavor so that we can then do the complex analysis part. But we're subtracting off the mean. And so this is going to give us something that has mean 0. It turns out if you have independent random variables, the variance of a sum is the sum of the variances. Each one of these has variance sigma squared. We have n of them. So the variance of this whole quantity is n sigma squared. Well, if I ask you how tall is the average American male? Anybody want to tell me roughly how tall the average American male is? 5'8". 5 feet 8 inches plus or minus 16 inches squared. Okay, good. You should all be looking shocked. Nobody should ever talk about measurements of someone's height with uncertainty in inches squared. Unless we're talking about, maybe after Thanksgiving and how much. But for the most part, when you're talking about heights, you should be talking about fluctuations in terms of the unit of measurement, inches. So the variance has the wrong units. If our initial unit is in inches, then the variance is in inches squared. The standard deviation, the square root, that's the correct unit to measure fluctuations. And that's going to be of size for here, sigma square root of n, because we're taking the square root of n sigma squared. So this quantity, the expected value of Zn is 0, and the variance of Zn is 1. So we're essentially normalizing things so that this quantity has mean 0, variance 1. We're trying to compare apples and apples. And essentially it goes as follows. If you've done physics, you can choose where you have ground 0. Why not choose ground 0 to be at a convenient place? If I'm going to look at a sum, why don't I just adjust my scale so that the sum has mean 0? And I can rescale my units so that it has variance 1. So we only really have to understand one kind of normal distribution, the standard normal. And we'll talk more about the standard normal in the next class. We still have a few minutes, and there's still like 1 or 2 more things we can do. But the idea is that this is a good quantity to study. And then what we can do is we can let z be n01. So this means it's a normal distribution with mean 0, variance 1. The density is fz of z will be 1 over square root of 2 pi e to the negative z squared over 2. What we would love to do is show that the density of Zn is converging to the density of Z. And if the densities converge, then this is converging to normal. It's very hard to work directly with the densities. You do not want to calculate the densities exactly in closed form. You want to approximate things. And rather than looking at the density, can anybody think of any function related to the density that might be worth looking at? Characteristic function. So we would want to either study maybe phi of Zn and show that that's converging to phi of Z. Or maybe the moment generating function of Zn and show that that's converging to the moment generating function of Z. And now you can begin to see where complex analysis is going to come into play. If we have convergence like this, does that imply that the densities converge? So we're looking at transforms of our quantities. We're not looking at the density directly, we're looking at a related quantity. And the hope is that if these are converging, then the underlying distributions must converge. Yes?
Why is it hard to show that the density converges as opposed to these other things?
It's very hard to work with the density in closed form. You have these convolutions, and you're going to have to do all these integrals. And so we've got 5 minutes left. There should just be enough time to hopefully answer your question as to why the moment generating functions and the characteristic functions are so much better. So this is, that's the moments. So again, we have a closed form expression for the convolution, but it's not necessarily easy to work with. So let's say x and y are independent and nice. Let's let z be x plus y. We want to calculate the moment generating function of z. This is going to be the expected value of e to the tz. Alright, this is going to be the integral from minus infinity to infinity of e to the tz fz of z dz. But we know what the density is. How do we get the density? How do we get the density? Z is x plus y. How do we get the density? This is just an integral, it's a convolution. So this is the integral from minus infinity to infinity of e to the tz, and then this is going to be the integral x goes from minus infinity to infinity of fx of x, fy of z minus x, dx, dz. Should we worry about things converging? Yes. If you shook your head no, this is a math class. We worry about these things. Are we going to do that in class? No. But you should at least be concerned and aware that you have to justify all the interchanges. So now if we look at this, we can write maybe z as z minus x plus x. Which integral do you want to do first, the z integral or the x integral? See, the x is hitting both functions. Z is only hitting this function. We want to do the z integral first. We don't know how to do many things. We switch the orders of integration, and we write z as z minus x plus x. And by writing it like that, this piece is going to now fit beautifully with that. And we will get an integral, x goes from minus infinity to infinity, and this is why I love putting subscripts on my integration. This function becomes e to the tx. Now I have an integral z goes from minus infinity to infinity of e to the t z minus x f y of z minus x dz fx of x dx. Well, now when you look at this integral, I can replace z minus x with y. And by definition, what does this integral become? We've got about 1 minute left. We're going to do this fast. What does this integral become? The moment generating function of y. Evaluated where? At t. And now we have e to the tx fx of x. That's the moment generating function of x. And so here's the big theorem. The moment generating function of x plus y at t is the moment generating function of x at t times the moment generating function of y at t. This is why we care about moment generating functions. This is why we don't analyze the densities directly. The moment generating function of a sum is the product of the moment generating functions. You know, this is where I really miss not having taken abstract algebra. But you can see this nice interchange. And the idea is, if x and y are the same, if x equals y as a special case, you get the moment generating function of x1 plus x2 of t will basically be the moment generating function of x1 of t squared. And if we had n copies of these, plus dot 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 plus with an n over here, it would just be the nth power. And now, rather than doing all those integrations, now we just have one nice function to look at. So again, I apologize for those of you who have taken probability with me. It's a brief blitzkrieg, but we need to get to the point where we can quickly prove the central limit thing, which we will do tomorrow, modulo results from complex analysis. And then we'll fill in those results from complex analysis, and we'll see how all this accumulation stuff actually comes into play. Okay.